Maya is a senior software engineer at Pivotal Cloud Foundry. It is her second time in India and the first time in Goa. So please welcome her. So Maya works on the cloud platform, Cloud Foundry team for Pivotal. And before that, she's worked as a consultant on a variety of different projects. So yeah, over to you.
All right, thank you. Hopefully my slides get working soon. Otherwise, this will be a very exciting presentation. All right, good news. We have slides. So my name is Maya Rosecrance. Thanks for the great introduction. Like I said, this is my second time in India. Today, we're going to talk about the Golang garbage collector. And as a quick disclaimer, I'm not in any way a garbage collection expert. I just think this is really an interesting topic. So the resources for this, I've read a bunch of the source code, seen pretty much every blog and talk that's been done on the garbage collector, and read the garbage collection handbook, and kind of here we are. So the point of any memory management system is to give you as a Golang application developer the illusion that there's infinite memory, right? So you can write kind of whatever, and hopefully you will never run into any sort of out-of-memory error. And so these three parts of it will kind of mirror in our talk. And kind of the size of this is about how much time we'll spend on each section. So to start off, we have this sort of contrived example. So we have this duck, and this Go routine will be issued a user stack. And what we'll see is that a stack frame is generated. Our factory function is also put on there. And we'll see our duck value object in that stack frame. When new duck returns, that stack frame will get popped off. The duck will get turned to main. And eventually, when main returns, the whole stack frame will be cleaned up. And the Go compiler does its best to allocate as much as possible to the stack. And that's because stack cleaning is very cheap and very efficient. So far, we have no garbage. If we modified this, though, to return a pointer, then we can start getting towards heap allocation. And this time, when main returns, we'll leave the duck around. So hooray, we have garbage. So this no inline is just so that the compiler won't do fancy things with this. So if I run this flag, I can actually see the escape analysis that my compiler does. And that bold line, you can see it go to the heap. So I've simplified the whole allocation image, and this is a little more representative of what it actually does. So the allocator uses a size-segregated span. In this case, there's about 70 of them. These are small object spans, and the sizes are determined by the compiler. And what it will do is when you ask it to allocate an object, it will try to find a page that has been picked to only contain objects of that exact same size. So both of these values here have the exact same size. And if it's larger than 32 kilobytes, it will be rounded up to the nearest page size. So each page is about 4 kilobytes. And then it will be given that many pages that it needs. And then there's the bitmap manager to kind of manage that. Interfaces, if they contain more than a machine word, will also get allocated to the heap. And there's a number of other things that will also be there. That said, I don't want anyone to come out of this thinking that they should prematurely optimize to write everything to the stack. I would wait until you kind of get to the end of this talk and you're starting to see bottlenecks. Another problem with allocating everything to the stack is that if you go from one stack frame and then allocate something and then go much further down, the object will stay around until the whole stack frame returns. So potentially, it becomes garbage fairly early in its life cycle, but won't be cleaned up until that whole stack frame gets cleaned up. OK, well, with that said, now that we have garbage, we can actually talk about the garbage collection algorithm. So it's a non-generational, non-moving, concurrent tricolor mark and sweep. Most of these algorithms were actually developed in the 70s, but like modifications and optimizations have happened up until now, really. So here's a brief timeline. The top is Golang versions, and then these are kind of things that have happened to it, and we'll kind of go through each step. All right, so mark and sweep collectors. If we have CS undergrads in here, this is the one they commonly teach. So at some point, it will trigger. We've reached whatever we say is our optimal heap size for the moment. And then we start a stop the world time. So this tells our program to stop running. You can't allocate anything. And now that I've got this nice definition of latency, this is latency. So from there, we'll start to mark our root objects. And root objects are our user stacks and our globals primarily. So we'll mark them. And then we'll start tracing the things they point to. And at that point, we've traced everything we can access, and we can delete any objects that aren't marked, the sweeping portion. Then we ask the question, can we shrink the stack? So if we're using less than a current of our current stack, we can shrink it. And kind of the minimum here is about 2 kilobytes. Everything that's left at this point, we call our live data set. And I use live and reachable sort of interchangeably, and then dead and unreachable. That would be our duck object that's gone. So kind of from here on out, we're going to focus on things that reduce that stop the time world as much as possible. Because you can see how that can really negatively affect your programs. And large programs, we're seeing as much as a second delay here. For completeness sake, there are 3 other basic algorithms. Mark compact is used in Lisp, and it does that same mark phase, but it will move, after the sweep phase, your objects to a different spot in the heap, side by side, so you're not ending up with holes in your memory. Copying, used in Haskell, instead of a mark phase, it just moves the objects themselves to a different point in the heap, and then kind of follows everything else as well into that new space. Reference counting, so the objects themselves keep track of whether they're used or not. And the danger here is you can have A that points to B that points back to A, and that loop will stay around indefinitely. Interesting enough, the Java runtime will kind of figure out which is the best algorithm of these 4 and kind of switch between them. Then there's also manual garbage collection is done with C, so malloc and free commands. There was a Java study done that they found that with sufficiently large heap sizes, so garbage collection isn't running that often, the garbage collector could outperform manual memory management because there's a little bit of overhead for these commands. And in the standard Java default case, it underperforms manual garbage collection by about 17%. OK, so those other algorithms do some form of compaction, or some of them do. And that's to avoid memory fragmentation. And memory fragmentation is bad because you end up with holes in your memory that you can't fit any other objects into. And you run into overhead because you have to ask each of these spaces, can I fit my object in you? Can I fit my object in you? And you kind of move down. So that introduces more latency in your allocation. So we get away with it here because we're using these size-segregated spans. So say we deleted that first value. Well, we know that it'll eventually get filled by something that's exactly that same size. We might get a little bit of internal fragmentation when we round up, but that is at most 4 kilobytes in our large object cases. And this might change. They might make it moving at some other point in the future. All right, so the next optimization they made was to make it tricolor mark and sweep. And this is to make it concurrent at some point. So the first version of this was a strong invariant version of the tricolor mark and sweep. So basically, no black node can point to a white node. So we start with our stop the time world again. We'll mark all our objects as white. This is kind of unscanned, potentially garbage. We'll mark our roots. And then in order to keep our invariant, we have to mark things as gray. So you can see we have our 3 colors here. Black, in this case, is we've scanned you, you're done. We won't look at you again this garbage collection cycle. Gray is we will scan you yet. And then white is we don't know yet. So we'll go through and eventually see it's done. All right, this is another way I've seen it visualized, and here you can kind of see the wave front progress. All right, now it changes to be a concurrent. So this is the 1.9 to modern version of this now. So we start the stop the time world, and then we put in a write barrier and a stack barrier. So the stack barrier, in this case, is saying, we're not going to let the program write until we finish scanning the current frame. So in this case, we're going to scan new moose. And then we can remove stop the time world, and then we can start proceeding. So the program, the mutator in this case, can continue to allocate. And the write barrier will say that while garbage collection is running, it's going to allocate black. It's a black mutator in this case. And so in this case, maybe the next command will remove the link to moose, but that's OK. We're going to catch it next garbage collection round. If for some reason we immediately return from new moose and move to moose maker, but we hadn't actually scanned that, the stack barrier will say, hey, you have to wait, program. And then eventually the stack barrier will go up and then kind of get the rest of the things on our stack. Then we have one more stop the time world at the end, and we remove the write barrier, and then we can do the sweeping in the background. So there's another case. We can allocate new objects, and we can allocate them black, but we can also mutate pointers to existing objects. I can do this, right? So this breaks our invariant. And 1.9 introduced a weak invariant. So a black object can point to a white object, so long as there is a gray path to that object. So in this case, we have goose that also points to that object. So we know that B can never point to duck because we don't have a reference to it anymore. So it's preserved. We can also, let's say we moved the pointer from goose to gosling over to B. In that case, our write barrier is actually smart enough to realize that it needs to color that. There's a few other things at play. There's the actual triggering of when garbage collection runs. And that is a knob we can tune in a few slides. And then there's the garbage collector pacer. So the garbage collector pacer is responsible for ensuring we don't run into concurrent mode failure. So basically, we're not generating more garbage than we can clean up. And what it does is it says that if a program is or a Go routine is particularly noisy in terms of allocation, it might pause that Go routine and use it as a marker. And so that way we kind of increase our garbage collection at the cost of your programs. So you can kind of see here that it's making trade-offs, right? We're going to have garbage collection run slightly longer so that we can reduce pause times, stop the world times as much as possible. We're also going to say that if garbage collection is running behind, we're going to sacrifice program throughput. So we're going to pause Go routines to run garbage collection. But at this point in time, I think pause times are well under a millisecond. So your program shouldn't be noticing these pause times as much. OK, then comes knobs. So we have one knob. And the idea here is that you shouldn't have to tune your program every time you switch hardware. So that one knob is called GC%. And this is to configure how often your program runs. So this is the ratio of freshly allocated data to live data. And so your live data is the stuff that survived your previous round of garbage collection. So if you set it to 100, functionally, it's when your heap size doubles. And there's just sweeping happening in the background, so it's not exactly when it doubles. But if you kind of ignore that, it's functionally when it doubles. So you can set it to off if you don't want to run garbage collection. You're going to manage it yourself. And you can also set it at runtime with debug.setGC%. And by tweaking this, you're changing the trade-off between CPU and RAM, right? If you run garbage collection less often, you're going to use more memory. If you run it more often, you're going to consume more CPU cycles. With 100, though, you're keeping the cost of allocation and garbage collection linear. So if I set it to 300, I would have double the size of the heap, and then I would run it half as often. And I've sort of rewritten the equation a few different ways because it took me time to wrap my mind around it, at least. And then if you set it to 50%, it would trigger at 75 megabytes. And so in this case, you're running more CPU cycles. So this GoMax prox is not directly related to garbage collection, but it is. So if you were running a totally serial program, you might think, oh, I can change GoMax prox to 1. But garbage collector threads pull from that as well. So you would be, in effect, taking on a lot of that latency. The garbage collector can run up to 8 threads, and by default, this number is set to the number of cores. So it's probably safe to just leave it alone unless you have a purposeful reason to change it. And it's actually in the code itself, it's slated to be removed at some point. There's also max heap size. So this I first heard mention of last January as something that was used internally. And the idea here is that what happens when we break the promise of infinite memory management, right? You run into out-of-memory errors, and that is a panic, which isn't great for production applications. So the idea is maybe you could set max heap size to your total RAM, and then it might put back pressure on your app to do more garbage collection cycles. The problem here is that if you set it to total RAM, well, your resident set size, sorry, is your heap, your stacks, and your globals. And your stacks, you don't really have a great handle on how big they are. You can get some similar behavior with tuning GC%, in that you can ask your runtime for how much memory it's using, and you can make garbage collection run more often as you reach that number. Kind of the last piece is to measure how you're actually doing. I just have a note to be a little bit wary about benchmarks you might find on the internet. And the thing is, because they might not act the way your actual programs are acting. So a lot of them have very small data sets, so they're going to trigger garbage collection more often than your program might actually do. That said, they can be very valuable for stress testing, or if you can find a benchmark that actually accurately represents how you're allocating data. So there are a few tools out in the wild to actually measure your performance and measure your bottlenecks. That's probably a totally different talk, but this is just like a kind of a brief introduction of those tools. I recommend looking through those 2 bottom links if you want to look through this more. But those can help you determine how you want to balance your trade-offs between memory and CPU. GC Trace is a very valuable tool specifically for garbage collection because it will show you your heap size before and after garbage collection, so you get an idea of your live data set. And it will also show you your stop the world time and how many workers had to be involved in your garbage collection. All right. And that's it. Thank you. I think we have some time for questions, if anyone's feeling like they have any. All right, then. Thank you.
So you mentioned that interfaces actually go on the heaps. But for testing, we kind of like promote people coding using interface. So what would be a good trade-off between like, should we use interface? How often we should use interfaces?
Oh, you should definitely use interfaces. I don't want anyone to come out of the talk saying like, oh, I'm not going to use pointers or interfaces. The only thing is you might want to reconsider how you use them if you notice a bottleneck, right? Like if that cost of, I wouldn't say interfaces are probably going to be that problematic, but I guess it really depends on your use case.
All right.
But writing garbage, you would have to do a lot to not write garbage. So in order to write idiomatic standard Go, you're just going to be generating garbage. Yeah.
Sure. Thanks.
So how are the garbage collectors getting triggered in the sense, is there any signal from the OS that it gets that, you know, it's filled up like 75 MB? So does it trigger or the garbage collector, does it register with the OS saying that, okay, when my program memory reaches this much, I need to be notified or something like that? Do you know anything about that?
Yeah, so there's a manual command to trigger it manually if you want to do that. But that set GC%, so when you finish a garbage collection round, it saves your live data set size. And then if you left it at default, it would trigger again when you've doubled that. So instead, it kind of sets this heap size that it's going, like a number it's going to run at when you hit that heap size. And you can change how large you want that heap size to be.
Okay, so it is going to look at some interrupts from the CPU or something. What's the exact mechanism that it uses? Like, does some of the libraries built within the Go program executable sort of look at it from time to time, pause the program and all that, or is it an event from the CPU that triggers this garbage collection?
To be honest, I don't know. No? Okay.
All right.
Maybe Bill Kennedy has more.
Yeah. Sweet. Sorry? Okay.
Okay, Bill Kennedy does the answer is the question.
Thanks.
All right. One more up here.
Great talk, thank you. Can you tell us a bit more about how you think about GC in your work at Cloud Foundry? Is that something you think about when you design your APIs and when you do all that stuff?
So at the moment, I'm writing a lot of Seago. So it hasn't really been a concern in my day-to-day development. Yeah.
Thank you.
The tricolor mark and sweep, what advantage does it provide? Why mark it as gray in the first place?
So that is pretty much to allow it to be concurrent. Yeah. Okay, thank you.